Uros Seljak today. Uros is a professor of physics and astronomy here at Berkeley. He's the senior faculty scientist at LBNL. I think he's the director of BCCP. And so Uros is a cosmologist who's really led a lot of seminal work in our field and studying the cosmic microwave background, studying general large-scale structure, as well as weak gravitational lensing. And I guess in 2019, he was inducted into the National Academy of Sciences. And in 2021, he was co-awarded the Gruber Prize for some work developing predictions and techniques to study the CMB and the universe in its earliest moments. And more recently, Uros has been working with collaborators on developing methods for accelerated Bayesian inference, also using machine learning for cosmology, astronomy, and broader science applications. And I'll just say, anybody that knows Uros or knows of Uros's work, I think would say that he's really a forward thinker. I think the same is true for the work that he's presenting today. And even though he's my supervisor, he didn't bribe me to say this. But yeah, I'm really happy to hear him talk today about gradient-based Monte Carlo sampling in very high dimensions. So let's welcome Uros.
Yeah, thank you. Why are we talking about forward models, right? So maybe not so much forward thinking, but forward models. Okay, so let me start with the introduction. Is this was working? Okay, never mind. Actually, I think I have a different problem here. So this is not. Okay, now it's working. Okay, good. Right. Okay, so let me introduce the problem first. What are we talking about when we talk about sampling? We are trying to get the probability distribution. We're trying to get particles or samples to follow a certain probability distribution. All right. In 1D, will be something like this, and there are methods that we know how to do this in 1D. But now think about these probability distributions in very, very high dimensions. This is very hard, right? Because we don't know where this distribution is, not only where it peaks, but how broad it is, okay? And so this is an important problem in many fields. Bayesian inference is one, but molecular dynamics is another one, statistical physics, lattice QCD, and so on. And some of us know this very well, that we tend to spend a lot of time waiting for Markov Chain Monte Carlo to finish, right? So we are literally burning a lot of time on supercomputers to get these posteriors very often and so on. Okay, so this is related to optimization, right? Because optimization would be the task of optimization would be to find the highest peak, or maybe multimodal distributions highest several peaks, but it is harder. Okay, so let me. Okay, so there's another point I want to make is. There are problems, hierarchical problems, and hierarchical Bayesian problems in particular, where the answer is very far from the peak. Okay, the center, the posterior center can be very, very far from the peak. So it's not just that this is in some sense a fancier version of the optimization. Sometimes actually, optimization will just give you completely wrong answers. Okay. Statisticians like to talk about examples such as Neyman-Scott paradox and stuff like that. But basically, this is in hierarchical problems, this happens all the time. All right. So in this context, we talk about typical set. So suppose we have just one peak. Then we have probability density, which peaks, let's say here. But then we also have the volume, right? So probability density is a point, so it has zero volume. Now we need to imagine you're spreading out the volume. Volume grows. And the typical set is where basically volume times, volume density times the probability density peak. So we call this a typical set. So typically would be some distance away from the mode. Mode will be the peak. All right. So, and in high dimensions, of course, this is this distance changes a function of dimensionality. Right. So this is what we sometimes call concentration measure. This is where all the action is happening. Okay. Again, just to mention these hierarchical problems, sometimes this volume actually depends on the parameters, hierarchical parameters themselves. And in that case, you need to account for that. So again, the reason why this is harder is because it's not just enough to find the peak, you also need to find the volume of the typical set. All right, so let me, so this is my, the outline of my talk. I'll go through a couple of first of all, I'll present you an introduction to these gradient-based methods. And now I'll talk about microcanonical approach that we developed in our group. I'll talk about metropolis adjustment, and then I'll talk about the tuning a lot. Okay, so the art of this field is more in terms of how you tune parameters, and I'll talk about which parameters need to be tuned and how modern methods do it. And then I'll talk about many applications in several different fields. And finally, I'll conclude with ensemble methods, which we are developing at the moment, which I think could take this field to another level. Okay, so I won't do much of a theoretical perspective here. It's mostly practitioner's point of view. And so the first question is why gradient based? It's because gradients are the only hope to achieve this in high dimensions, right? It's very similar to optimization, right? Optimization in high dimensions. If you don't have a gradient, you're lost, and similar situation happens here. Okay, another reason, however, for gradient is that modern languages, such as, let's say, JAX, actually have built-in autodiff and stuff like that. And it's actually very easy to get gradients, right? And so that's another, more modern perspective of that. So we actually get grades for free. All right, so let me start with Hamiltonian Monte Carlo. This is an example of a canonical probability distribution. What do I mean by that? I mean by that we write the probability distribution of position and momentum. We introduce a momentum particle, so we write it as a Boltzmann factor e to the minus h, where h is the Hamiltonian, so basically this is the energy. And then the Hamiltonian itself is kinetic energy plus potential energy. And here we write potential energy as a log of the gradient of the target, T of x. And so what we do is we run this, so think of this x and momentum, pi. We run this Hamiltonian dynamics for a while, then we resample the momentum, and we run it for a while again, we resample the momentum, and so on, okay? Once you project this, you marginalize over the momentum, you only project over x, you get the target distribution, all right? So that's a very nice way to achieve the target distribution, and has been a workhorse of basic gradient-based methods for decades now. Okay, let me now quickly introduce the new method, which we call Microcanonical Hamiltonian Monte Carlo, which asks the following question. So rather than having canonical distribution, so with the Boltzmann factor, can we achieve the same goal by with a microcanonical distribution where the energy is actually conserved? So this is again another Hamiltonian minus the energy, let's say. And so now, in this case, we would like the joint distribution of position momentum to be basically constant energy. Can we still achieve the same target distribution? The answer is yes. However, what is needed in that case is that the kinetic energy is modified. Instead of being momentum square, it actually turns out to be log of momentum square, and some additional prefactors. Okay, so it's a very different kinetic energy. And this is actually related to isokinetic Monte Carlo, developed by Mark Tuckerman and his group. But I'll talk about where things get more interesting and more complicated, because just having this dynamics is not enough. We need to also have some noise. All right, so I do have two. Yeah, go ahead.
Is there any intuition? Maybe I'm just completely missing, but I kind of tend to think that in the Hamiltonian, right, the kinetic part is kind of somewhat tied to the structure of the polar Lagrange coefficient and kind of the symplectic structure of the dynamics, and that the potential is where we have a lot of freedom. But like, do you have any intuition on what does that log do, or is it just a mathematical trick to solve this problem, or is there any?
Well, I mean, for this particular case, it is just something that once you project over it, you get distribution. But now I want to show you actually the dynamics, how the dynamics differ. Okay, let me start with this one, the left side. So this is Hamiltonian dynamics.
With the standard kinetic energy.
With the standard kinetic energy. And so what you see is slow on the edges and goes fast to the center, right? That's, this is not what you want really, because if you take the samples of this, it will not give you the target distribution, right? In fact, the target distribution should spend most of the time more here in the center. Instead, this particle is going very fast to the center, right? So how does the Hamiltonian achieve this? By also resampling the momentum. In contrast, the microcanonical one actually does what you would expect intuitively, right? So it actually is slow here in the center and very fast on the edges. In other words, this dynamics actually, the stationary solution of this dynamics is already a target distribution, even without any momentum resampling. Okay, so that's the one difference between these two the dynamics.
And does that mean that this would be? Is there an equivalent Hamiltonian that's still conservative that would have a standard kinetic energy, but basically that would have some additional conservative force that would do that? Like, is there an equivalent Hamiltonian with some other conjugate momenta where the force would give that dynamic?
No, not to my knowledge, no. Okay, so
In this example, there is single.
yeah, multimodality, I mean, all of these methods struggle with multimodality. So in other words, they can go between multimodal solutions if they're close enough, but if they're very far apart, then these methods fail. And so in that case, you need to do other things such as annealing or tempering in order to solve it. Okay, so
there's something I also don't understand. So in this Hamiltonian microcanonical ensemble, you still have conservation of energy.
total energy, yes.
Therefore, how? But still it converges to a point where the momentum is zero and where you sort of stuck in the middle. So
No, momentum could be anything you want, right? It's never zero,
in
really.
your picture, you seem to indicate that eventually spends most of the time in the middle, which seems strange to me because by conservation, I can't imagine that the momentum ever dies out because it
Yeah, momentum is never zero.
so it doesn't really reach the minimum.
No, it doesn't. It moves around all the time. But in fact, I'm going to reformulate this in a simple formulation, which is where actually velocity is constant. So yeah.
Sorry, but yeah, I mean, what I was asking is like, sure, if they are totally separated, so there's nothing you can do. But if they are not entirely, I mean, I wonder if there is trade-off between the two, because this one spends less of the time exploring.
I mean,
Is it less likely to find
on multimodality? I think they're both equally good or bad. Yeah. So I don't think the advantage of microcanonical is in multimodality, but it has other advantages which I'll get to. Okay, so again, the problem with this microcanonical or canonical is that the station target is achieved. However, you still need to introduce some noise, momentary sampling in order to achieve ergodicity. So what is ergodicity? Basically is the fact that you need to get into all corners of the parameter space. And due to the various conservation laws and stuff like that, if you have just deterministic dynamics, this will not happen, right? So you need to kick it around, and that's where we introduce the noise, okay, into these dynamics. And then we also, as I said, we reformulate into a form which has a constant velocity. So the way to think about this is basically we are just doing momentum resampling or velocity resampling on a sphere, right? So velocity, the length of velocity is always the same, and that actually does have some advantages, which I'll explain later what they are. Okay, so let me talk now about Langevin dynamics. Now, so very often in literature, Langevin and Hamiltonian dynamics are presented as very different. Okay, so let me just remind you what is underlying Langevin dynamics. It's a stochastic dynamics in this case. We have an additional stochastic term, which is noise. And this noise, what it does is that it achieves ergodicity, right? Again, you need to kick the stuff around in order to achieve all possible configurations. So this term gradient keeps you to stay, forces you to stay on the typical set. This term here explores the typical set and moves around, right? So, but you probably have heard of fluctuation dissipation theorem, which says that whenever you have fluctuations, you also need dissipation. And so that's what this term here. So there's another damping term here in the Langevin dynamics that satisfies that theorem. Now let's look at the same picture in this microcanonical Langevin approach. Here, this is the equation. It's still a secondary equation, but you see, and we still have noise, but this noise now is on a sphere, on the velocity sphere, and there's no dissipation because we're literally conserving, forcing velocity to be one all the time.
What do you mean x dot squared?
Where? Here?
X dot times x dot.
Yeah, we think of these as vectors, right? That's why.
I see. So it's a
Yeah, right. This is just projector in order to force velocity to be one.
Oh, it's not the atom. It's a projection onto x dot.
Yeah. Right. Yeah. This term enforces that velocity is one. Okay. So right. So this is now the Langevin dynamics. And what's the difference between Langevin and Hamiltonian dynamics? Well, in literature they appear as two very different methods, but they're not actually that different, right? In one case, the way to think about this in Hamiltonian dynamics, you follow some steps and then you completely resample the momentum. And in Langevin dynamics, you kick with less noise the momentum, but the net effect is essentially the same, right? So these two Langevin and Hamiltonian dynamics are very similar to each other. In both cases, we define basically a typical trajectory length, let's call it L, over which the momentum has been basically resampled. Okay, so there is one limit of the Langevin, which is overdamped limit, where actually you get rid of velocity. It becomes a first order equation. This is an overdamped limit. This is far from optimal, but I just want to mention it because some in statistics, for example, MALA is metropolis adjusted Langevin method. Usually works in this limit, but it really is suboptimal compared to this fully second order dynamics. Okay, so I'm not going to talk much about ergodicity. Let me just say there are ergodicity theorems for these methods. And so these methods do, achieve ergodicity. And so I forgot to mention in the beginning, in my talk, I won't mention Nose-Hoover thermostats, but I just want to emphasize Nose-Hoover thermostats in their original form are not ergodic. Okay, so there's no theorem that proves ergodicity. And even if you have a Nose-Hoover chain, again, there's no theorem that those systems are ergodic, so use them at your own peril, I think, but they are heavily used in molecular dynamics, right? So ignoring this fact that they're not ergodic. Okay, so there's another thing that we sometimes like to do, metropolis adjustment. Okay, so what is metropolis algorithm? Is the first algorithm that was proposed in the MCMC, which was you propose the next state, you try to move into the next state, you ask what the, for example, energy is of the next state relative to the current state, and if the energy goes down, then you accept it with some probability, and if it goes up, then the other one. If it goes up, then you accept it with some probability. If it goes down, you always accept it. Okay, in the context of this gradient-based method, since we have a Hamiltonian, we have the energy. The methods that I've described so far would have been perfect without any error if it weren't for the discretization error, the fact that we have to discretize the orbits. And so there is some error that we induce due to discretization, and we can correct, using this metropolis algorithm, we can correct for that error. We can remove the bias, basically, of these methods by metropolizing, as we sometimes say, by applying this metropolis adjustment. Okay, and so every method that I mentioned before has its own metropolis version. Hamiltonian Monte Carlo actually typically is already with this accept reject metropolis step. MALA I mentioned is metropolis adjusted, right? MOLS, metropolis adjusted, Langevin, and stuff like that. Okay, so there's a whole bunch of methods, including ours, microcanonical methods, which have metropolis adjustment step.
The metropolis adjustment makes a non-ergodic algorithm.
No, metropolis adjustment has not much to do with ergodicity. It has to do with the bias. Let me this explain on this. Okay, so basically think of it, if you're doing an ODE system and you have a finite step size, the target distribution will not be exactly the distribution you want to achieve. It will be something else, right? Sometimes in the case of Hamiltonian Monte Carlo, we talk about shadow Hamiltonians. So you achieve the target, which is shadow Hamiltonian target, not the target you wanted to have. So basically, there's a bias there, right? You're converging to a distribution which is not exactly the target distribution. Okay, so that's the bias we're talking about. And we all know, right, that any error can be split into bias and the variance, right? So on top of that, we have the standard variance term. We typically have a typical number of effective samples. Often we like to achieve 100 or 200 effective samples. And so there is always some variance term. So now the question is, if you do metropolis adjustment, you essentially, by construction, completely eliminate this term. But by doing that, you actually increase this term, and I explain why, okay? And so here is basically our plot, right? What are the typical biases that we have in these methods? There is the internalization bias, we call this burn-in, right? Which, if you start sufficiently close, it will be very small. And then there will be some variance error. On the other hand, but there will be no bias if you have adjustment, metropolis adjustment. On the other hand, if you don't have metropolis adjustment, maybe you will pick up another term, which is bias term, but potentially this could actually be, this plus the variance term could actually be smaller than the error we're making on adjusted methods. Okay, so this is the trade-off that I want to explain a bit more about this, right? How this trade-off works in practice. Okay, so right. So the question therefore is metropolis adjustment, is it a curse or a blessing? And as I just explained, right, if you have adjustment, then its bias can be 0. But if you don't have adjustment, bias is not 0, but it actually scales very steeply with the step size for second order integrator. In fact, even steeper for higher order integrators. And so it's quite possible that no adjustment actually can be better than adjustment. All right, so I'm going to look now at these trade-offs in practice. Before I do that, I just want to say how we usually define the error. We like to look at the error of the second moment. Why second moment? Well, I mean, typically, a second moment of what, right? Typically, we have, we like to know the marginals. You know, we'd say, you know, maybe we need to sample over 100 parameters, maybe just a few of those parameters we actually care about. So these are the posterior marginals we want to look at. And of course, typically the first thing we want to look at is the mean and the variance. And so this number here, then, you know, the mean square is incorporates the error on both of these parameters. So basically, this is how we define this bias. And, you know, for a Gaussian distribution, we typically like to achieve the bias of order 0.1. And that translates, if the only error is variance, that translates into 200 effective sample size, right? So basically you have 200 effective particles. Okay, so that's what we like to look at. And I want to emphasize margins are hard, right? Margins are 1D distributions, margins over everything else. You need to get the full distribution right in order to get that one distribution right? So they're hard. This is not a trivial task here. Okay, so can we estimate the bias from the RNG error? Okay, that was the question we asked. So sure, maybe we don't want to have bias to be 0, but can we at least estimate what the bias is? And it turns out that the error, the energy error per dimension, or this EVPD, you know, gives us some estimate for Gaussian targets. We have basically a bound of how the bias for a Gaussian distribution relates to the energy error. Okay, so this is for Gaussians, and now then we looked at, well, you know, how good is this bound in the case of real distributions. And by the way, we also have similar results for Wasserstein distances, but okay, I'm not going into details. But basically, here's this bound, the black solid line. Standard Gaussian is blue. You see it's below the bound. A very ill-conditioned Gaussian with a condition number of 1,000 is this one, so it's very similar. We can see most of these curves are below the bound, but there are some exceptions, right? So this doesn't work perfectly, but it works pretty close. And so we're going to be estimating using this energy error relation relative to the bias as an estimate of what the bias is.
So if you have counterexamples to your bound, what were the hidden assumptions which makes the bound not true?
No, yeah, I mean, as I said, the bound was derived only for Gaussians, right? So we have we don't claim that this is a real bound, but on practical examples, it does seem that even hard distributions like, I don't know, here we have Rosenbrock and funnel, you know, these are very hard distributions. I'll show some of those later. You know, this still is, you know, roughly satisfied. So basically what we decided, okay, you know, as long as we take this EVPD sufficiently small, let's say 10⁻⁴, then the error is, then the bias will be so much smaller than the target error that we are fine. Okay, so that's our proposal. So this is how we choose the step size, right? Okay, so the second parameter that we need to determine, which is how long should these trajectories be? Either in Hamiltonian Monte Carlo, how long the trajectory is before we momentarily sample, or in the case of Langevin, what's the amount of noise such that after, you know, L steps, we have fully resampled the momentum. So tuning this parameter has been really, really hard in the literature, but it's really crucial. If this parameter is too short, then the methods are inefficient. If it's too long, they're inefficient. So really, it's extremely important to get it right. And the current state of the art, which is no U-turn sampler, does this by looking at when these orbits of the trajectories turn around. But in order to do that, I actually need to, you know, run these particles in two opposite directions and stuff like that. So they're paying quite a large price already from the beginning, typically a factor of 2.5. Okay, so Our proposed alternative is this alpha autocorrelation length-based adaptation, and we say, okay, we're going to look at the correlation length, which is often looked into in MCMC methods, and then we're going to set this L to be some fraction, typically a half of that correlation length. So, and by doing that, actually, it turns out that even though this is a black box tuning, we get extremely close to the grid search solutions. In other words, this is very, very close to optimal solution as well. So this is how we now have tuned the second parameter. Let me just tell you quickly. Okay, and so here, for example, are some of these examples how well we're doing with metropolis adjustment compared to nuts, and very often we are a lot faster. And in particular, there's one problem, funnel problem, where the solution looks like this, which is famously known because a Hamiltonian Monte Carlo methods just fail; they never converge. The problem is they don't get into this throat. And the reason that microcanonical versions don't fail is this constant velocity, which then prevents these particles from flying off too far if you have a large error. Okay, so this is what for say equal number of steps. This is what unadjusted Langevin Monte Carlo did, and this is what Microcanonical Langevin Monte Carlo did, and you can see MCLMC sampled a lot better than Langevin Monte Carlo. Okay, so right, so this is maybe an extreme example, but an example that is very often used in the literature as a very
So just so I understand, the two figures at the bottom, the total length of the trajectory and time
it's the
distance is the same.
Yeah.
So the difference is this one somehow managed to basically bounce forever.
It took forever.
And this one went straight out.
Yeah.
So it spent its time sample this side.
Right. Okay, so another issue that is important for this question of adjustment versus non-adjustment is performance as a function of dimensionality. And this is where the argument for unadjusted methods really comes through. Basically, unadjusted methods are essentially dimensionality independent, whereas the adjusted methods, because the step size has to shrink, because the acceptance rate gets harder and harder to satisfy, you need to shrink the step size, and therefore it takes longer to explore. These scale as d to the 1/4. These are independent. Okay, and as a result, if you go to very high dimensions, you start seeing orders of magnitude differences between the methods. In other words, unadjusted methods start winning very, very strongly in high dimensions. And this is true for Gaussian distribution. This is a Rosenbrock, basically a more complicated distribution, right? We see this d to the 1/4 scaling always for the adjusted methods, but not for the unadjusted methods. Okay, so now I'm going to show you a couple of these comparisons of different sorts. First of all, this is without adjustment, this is with adjustment, lower is better. And it's not true that always these methods win. For example, Hamiltonian Monte Carlo and Langevin Monte Carlo are these methods, blue, right? Whereas microcanonical methods are here. You see, typically microcanonical methods are better than canonical methods. And they're also typically better than nuts, right? So this would be the current state of the art, right? And but often, as I said, the microcanonical methods shine without adjustment. So this is a lot lower than this. By the way, this is a Cauchy distribution. It's an example of a fat tails, and in the fat tails, these microcanonical methods really explore the tails a lot better. This is an item response. It's in one of the higher dimensional hierarchical Bayesian methods problems. Sorry. Okay, so these are a couple of examples. I have a whole bunch of other examples. I'll talk about them, but again, just to show you an example of a fat tail Cauchy distribution, right? So very, very fat tails. Same number of samples here. Microcanonical version has really populated the tails very well, whereas the nuts just barely is doing anything, right? And so it's a lot worse. And so here's a plot of the bias as a function of gradient calls. And in this case, again, nuts hasn't really converged to our target bias, whereas here we have converged with about 10 to the 4, a few times 10 to the 4 calls. Okay, I'm going to talk about some of these examples here.
So I have a question in German for that. So all your problems are those where actually your mixing time is probably polynomial, the size of your problem.
What is the mixing time here?
The time it takes for your chain to actually come to equilibrium. That's so is that how that does, for example, if you have a dimension here, does it grow exponentially in the dimension? Does it typically grow like a power of the dimension?
That time, let's see, I think I had it somewhere. Sorry, yeah. This is this, I think you're talking about initialization bias, right? This is initial time. This is, we call it burning. This time is actually exponential. It's not polynomial. It's actually exponentially approaching. So that's why we usually don't worry about this time, right? Because it's exponential. Now, of course, prefactor could be large.
Monte Carlo for easing models here's a critical point, or whereas in the low temperature region, I often have it takes exponential time to burn in because I have to sort of work through this interface between pluses and minuses. And so in many real life problems, what we call the trivial burn-in time is actually sort of makes a problem sometimes NP hops.
I would call the problem you're raising the high condition number problem. I have slides on that. So I have slides on Ising and stuff like that. So okay, so let's talk about applications. Indeed, right? Let's talk about applications. I'll start with some cosmology applications, then I'll show you some Bayesian neural network applications, then I'll talk about statistical physics, which is the example you're talking about. Okay, so cosmology first. In cosmology, we like to do what we call field level inference. So cosmology, basically a picture of cosmology, we start with some initial conditions which are Gaussian. We now have a forward model, which is some extremely expensive n-body simulation plus some galaxy formation model. And this is how we go with a forward model from initial conditions to the data. Okay, our task is actually to go back from this to the field level initial conditions, but also determine hierarchical parameters such as forward model parameters, what, for example, matter density, or cosmology parameters which are imprinted in these initial conditions. I don't know, amplitude of these initial conditions and stuff like that. Okay, so these are a very expensive and hard hierarchical Bayesian problem. And it takes, I guess, three things. One is the forward model. So we start from initial conditions and body simulation. So we solve it's a gravity solver plus some galaxy formation model. This part we worked hard over by now almost a decade, working hard with developing various codes to make it fast and to make it differentiable. Okay, so this has been a program that we followed for many years. So now we actually do have. Just to give you an example, we can do 512 cube particles. So basically, 10 to the 8 particles, 100 million particles on NERSC. In each step is 1 second. And maybe we just need 10 steps. So in 10 seconds, we can run a full n-body simulation with gradients, right? So this is how far we have come over the years, right? This problem is now sufficiently solved that we can actually hope to do this inverse problem. Okay, so that's the inverse problem. Sorry, that's the forward model. Yeah.
Those codes, the forward model is a kind of standard numerical code. It's been implemented with JAX or something else that gives you the autodiff. But the forward code, you don't have a neural net in the forward code.
There's no neural net.
It's straight up.
No, yeah, it's particle mesh,
Yeah.
right? So yeah, with autodiff, yeah.
When you say it takes a second, that means on just one node or on
these are on one node. Yeah, exactly. This would in fact, getting across the nodes is hard. I'll get back to that question when I talk about ensembling and parallel calculations, right? Okay, so the actual problem can be, as I said, can be phrased in terms of hierarchical problem, right? So you have data, you have a forward model which starts from initial conditions as it has some cosmological parameter dependencies, right? And then then you have noise. This is the likelihood term, right? On top of that, you have the prior term, which is that the initial conditions are drawn from some Gaussian prior with some initial power spectrum, which also depends on cosmological parameters. Okay, so these are our joint distribution, right? So it's prior times the likelihood, log of that. And so this is what we're trying to sample.
how does K enter this thing in the middle?
Sorry, which one?
You have a sub K there. So the K.
Oh yeah, okay. Think of this as the sum in the Fourier space, so that everything has been Fourier transformed. So the data are in Fourier space. Everything is in, yeah, and so K would be the vector. Okay, so what are the challenges, right? We need a fast order model. I described that in the previous slide. We need a differentiable form model. I described that in the previous slide. And then finally, we need a fast sampler, right? That's also equally important, right? And so just going to give you a couple of examples of the current state of the art. This is actually not our work. This is a French group. And they tried several of these samplers on cosmology parameters, on the initial conditions, on the galaxy bias. In all cases, as you can see, MCLMC is about an order or and a half magnitudes faster than nuts.
So to do your Bayesian updates, you do gradient descent, or how do you do?
Yes, as I said, this is why I mentioned that it's really important that we have gradients of the data of the forward model with respect to initial conditions. But really think about this. This is a gradient. This is a 10 to the 8 dimensional gradient.
So, and I should imagine that one step is just one gradient descent, or do you want your gradient descent to? I mean, what is
the gradient is auto diffing through the full n-body simulation, right? So through all those 10 steps. Okay, so this is one example. Then another example that I'm really happy how well it came out, how it's coming out, is the example of cosmic micro background anisotropies. And in particular, there's this effect called gravitational lensing of cosmic micro background anisotropies. Basically, cosmic micro background anisotropies is a Gaussian field initially, right? But then as light propagates the universe, it gets deflected. And it creates these very specific distortions that can actually be modeled as a forward model. And so here, the likelihood the joint distribution is the joint distribution of a whole bunch of terms. So first of all, we have the data. In this case, CMB polarization data. There's a spin-2 field, so it has two components. So that's this F. Then we have the stuff that actually creates the gradation lensing deflection, and that's this field phi. Then we have the data X. So this is the likelihood term. This is the prior on the CMB field. This is the prior on the lensing field. Okay. And we sample all of this. And again, we're doing this right now. We're doing this in 512 square, times 3 or 4 fields. So again, we're talking about millions of dimensions in this case. This is not just theory these days. This actually also has been implemented in real data. SPT analysis, for example, has used a method that we have developed previously called Muse. I won't go into details, but it's a precursor to these methods. And they find amazing results. For example, they recover this CMB field, 11 peaks of this CMB field. They recover this lensing potential and stuff like that. Okay, but where we're going now with this is instead of having this approximate Muse method, we are now developing this with this Microcanonical Langevin Monte Carlo. This work led by Zach Lee, and this effective sample size per gradient, so higher is better in this case. And you can see basically MCLMC and Muse are roughly comparable in this case, and again, a lot faster than Hamiltonian Monte Carlo, right? And so the fact that these two are comparable means that we can actually solve this problem now with sampling rather than these approximate methods. And so this, I think, will be used a lot in the future because these methods are quite a lot more powerful, at least for these very low noise CMB experiments than the current methods that people use. Okay, so let me move now to the applications, field theory applications. A classic example is the Ising spin model, which can be actually converted into continuous field. And a simple version of that is phi to the 4 theory. It has this kind of action. And, as was mentioned earlier, basically think of it at low temperatures as ordered phase, right? So all the spins are pointing in the same direction. Then you have some phase transition at some point, and then all the spins are kind of randomly pointed, right? And so the phase transition is the thing that is hard to get. This is during the phase transition you get these very long range correlations, right? And so and that's what makes the problem very hard, right? Okay, so here are plots of susceptibility, which is standard quantity one looks like at. This comparison between let's say very long HMC chain versus MCLMC. The point is just that we recover the correct susceptibility. But again, if you look at effective sample size per gradient, right? So the higher the better, right? So you see here we have numbers like 0.3 and they're almost dimensionality independent, whereas here For nuts, for example, or HMC, the numbers are a lot lower, and the higher dimensionality we go to, the lower they get. So again, because of the metropolis adjustment, these methods really start to become very slow in high dimensions, whereas unadjusted methods don't. All right, so again, this is basically the same plot. Yeah.
So for the easing model, I'm not that astonished you might get around slowing down because there are algorithms which sort of, I mean, in the computer science sense, it's polynomial and not NP complete. But then you could have other models like hard spheres or so where actually the transition is NP complete. So I would expect that in general you would get slowing down.
But we are getting slowing down. Sorry.
Just say no critical slowing down.
No, I didn't say that. Sorry, I didn't emphasize slowing
There's
down.
no evidence
This
of
is the phase
slowing
transition. So you see how it has slowed down, right? So
Oh, so this
Yeah.
tendency I should.
this is a slowing down. This is a critical point, right? So it has gone down. So certainly above the critical temperature, sampling is a lot easier than other critical temperature. But then also below the critical temperature is also hard, right? Because it's multimodal, right? So often. So but you see, it's even more dramatic for nuts, right? How this slowing down happens at the critical point. So there's no question that there is slowing down at the critical
So
point.
this last paragraph there I should. It says no evidence of.
Oh, I see. Right. Yeah, okay, some evidence, I guess. True. Okay, right. Okay, so you're arguing about this particular example. Yeah, so slowing down is not too bad here. Yeah, I actually have a quantum Monte Carlo example where I think we see it slowing down a lot as well. Okay, so here I have a couple of other examples like U1, which is a toy model for lattice QCD, and 504. Again, the point is orders of magnitude faster, can be orders of magnitude faster.
One way that I would phrase like the question about the discrepancy between is the difference in slowing down at critical phase transition between the two approaches simply a constant, or is there something more interesting happening where this has at least better functional dependence on slowing down with, say, dimensionality, or say in QCD like fermion naked quark masses or things like that? Because that's really where it gets nasty, right?
Right. No, I agree, and which is why I think this example is more relevant, because this actually is basically spin fermion model. Has bosons, has fermions, has all of these big determinant with gradient descent, with conjugate gradient, exactly, right? And it doesn't have a sign problem, so you can actually do it with sampling, right? So I think this one is the closest that we have gotten so far towards lattice QCD, because lattice QCD people are very skeptical about not doing adjustment, right? So this is now work together with Peter Lund's group. On trying an example of that. And okay, first of all, here's susceptibility. This is the critical point. This is microcanonical. This is Langevin or Hamiltonian Monte Carlo. Basically, there's no difference. So we do get good agreement between the methods. Now, in terms of critical slowing down, this is again same plot as I was showing before. You see how effective sample size per gradient goes down. So the scale is slowing down, critical slowing down to this critical point, and then maybe it goes up, right? So things are definitely the hardest at the phase transition. At the critical, well, it's not quite phase transition, right? Because it's a quantum system, but anyway, there's some criticality here. So this is what we have, and this is 16 cube lattice with, I think we always do 40 time steps in this case. So for those of you who don't know, this is basically a path integral formulation. It's kind of lattice QCD, right? So you put everything on a lattice, but you also discretize time. Measuring time lattice, and you're doing kind of path integral. And so, as I said, it's similar to lattice QCD. In this particular example, it's particularly similar because it has both bosons and fermions.
And it's similar in the sense that your discretization is keeping the group symmetries correct and all that. The way that it has to be done in the standard lattice QCD formulation.
Yes. Of course, the details are different, right? This is not a lattice QCD, but yeah.
We have the fermion doubling problem people have in lattice QCD.
Well, I don't know what fermion doubling problem is. I know there's a fermion.
Depending how you count, the freedoms of the fermion sort of come out too large in standard
I'm not familiar with that one. Okay, so as I said, lattice QCD and this problem doesn't have sign problem, but it does certainly have this critical slowing down problem.
As Fernando mentioned, right, we have sort of many symmetries we would like, and sort of it's hard to not break all of them without introducing serious extra family.
Yeah, okay. This is not full lattice QCD, right? No question about it, right? We don't have a lot of things that lattice QCD has, but at least it's a first step in that direction. But again, the point is there's a performance is again between 3 and 5 to 30 times better for these microcanonical unadjusted methods. Okay, Bayesian neural networks, for those of you who are interested in that stuff. So neural networks have had tremendous success, right? And but nevertheless, there is some evidence that often, if you ensemble neural network solutions, that you get better results. This goes under the name of deep ensembles. And typically what ensembling means that you just start different initial conditions and then you average them, or maybe sometimes you select according to performance, things like that. Now, a slightly more principled way to go about it is Bayesian neural networks, right? Where you say, okay, I'm going to have some prior on these neural networks, coefficients, and the end is I will be sampling, right? So it's again a form of ensembling, which is more principled a bit, modulo questions of how you choose the prior. But the problem with Bayesian neural networks is that they're extremely slow in this very high dimension, all right? So what we have tried in this case is apply this Microcanonical Langevin Monte Carlo to Bayesian neural networks, and we have shown that you kind of, in these particular examples, and I won't go into details, these are UCI, standard UCI examples, that you get best of both worlds. In other words, you get something where the runtime is comparable to deep ensembles, but performance is better than deep ensembles, okay? So, of course, a lot of people in machine learning, in AI, they're skeptical of Bayesian approaches, right? And I share a lot of those skepticisms, but nevertheless, practitioners actually themselves often do try ensembling. This is one of the standard things you try, right? And so I guess our point here is, well, why not try Bayesian neural network instead with these new samplers, which are just as fast as ensemble methods. Okay, and so finally, in my last few minutes, I just want to quickly mention that MCLMC or MCMC is a good optimizer. So this is what Hamiltonian Monte Carlo trajectory would be doing, right? If you don't resample the momentum, it would just be, oscillating around here. We won't descend down there. This one just goes to the center and then goes straight down. Okay, so it's very good optimized. In other words, very good burning. And this is shown. Number of steps, MCHMC, for example, goes down to the typical set very, very fast. Okay, so we try to take advantage of this by developing this ensemble method, where we say, okay, we have a very fast burn-in. We don't care about adjustment in the beginning. We just need to get into the typical set. So let's have a phase where, let's start with large number of particles. Let's have a phase where we're just doing the burn-in. Once we are in a typical set, according to our prescriptions, then we switch to metropolis adjustment to eliminate the bias. And then this is what we get, right? And so, for example, here I'm showing the bias, right? As a function of number of gradient evaluations. And so in some ways, this gives us the best of both worlds. On top of that, we also use these ensembles for mass matrix preconditioning, right? So basically, often these methods do gain if you precondition the mass matrix, and so you can do with ensembles a lot better. Just to give an example of banana, right? You start with this very broad prior relative to the banana. This will happen after 5 calls. After 10 calls, you already are tracing banana very well. After 20 calls, you're done, right? So this really can be extremely fast in terms of wall clock time. And so, in fact, these are the numbers for the wall clock time. As I said, banana is about 20 calls to get the low bias. You see, even the most expensive ones would be, a few hundred maybe or 1,000. But this will be the typical number of calls for nuts. And these are calls in nuts parallel version, right? We're still running 1,000 particles, but it still takes a lot longer. And these are some of the other methods people have developed. So we think this is, current state of the art in terms of wall clock time ensemble methods. They outperforms other methods. And, if you care about wall clock time, and if you do this on a GPUs, as we know, right, you can run thousands of processors at no cost, right? Thousands of particles, right? And so these kind of methods really take advantage of GPU architectures and can give you orders of magnitude accelerations in terms of wall clock time, right? So for cheap problems where memory is not an issue, this can really be a very powerful alternative to get posteriors very, very quickly. And here is just a plot showing that as we scale up the number of particles, right, we don't lose performance. Again, this is on a GPU. In this case, again, this is because running 4,000 particles or 100 particles on GPU is exactly the same. GPUs can handle this kind of numbers of particles. All right, so how to run MCLMC? Well, you can take this picture if you want, but basically you just need to write down log density in JAX, or you can go to NumPyro and then you can run it in blackjacks, and that's it. So we have implementation blackjacks. We also have some wrappers for NumPyro and stuff like that, but basically blackjacks is all you need. Right, so that's a summary. I won't go into the details now, but I just want to say we're always looking for additional applications, especially in high dimensions. So if you have some, please reach out. Yeah, I'll leave the summary here. I'll stop here. That's it.
Great talk. We have time for a couple questions. So
the microcanonical approach itself is Markovian. You only care about the one previous step. It wasn't clear to me, did you break that with ALBA, or is that something you need to put in?
No, you're not breaking that with ALBA. ALBA is tuning, right? So the way to think about this, you tune the number of the step size, and you tune the trajectory length. You pre-tune that, and then you fix those, and then you run it at fixed.
There are other problems where you want to be non-Markovian, where you do care about not just the previous step, but you want the sort of global picture.
Yeah, people have been playing, for example, with adjustable step size, right? That would be an example of that, right? Adjustable as a function of local environment, local curvature, and things like that, right? And it gets very complicated precisely for the reasons you're saying, right? That how do you preserve Markovian? How do you satisfy the theorems, right? So it gets hard. So not sure I'm answering your question, but
take a cosmological example. For example, when you're in nonlinear evolution, you might care about tidal fields. Okay, you're not just caring about things that are local in space and time.
okay.
Isn't there some?
Well, I don't know. Maybe that has more to do with the loss function that you're asking. But I mean, likelihood is the optimal loss function in a sense. It compares data to the model, and there's nothing better you can do. No, so I think.
How do you adjust the step size, which you mentioned, step size?
I relate it to the energy error, and then I say, okay, this energy error of 10 to the minus 4 is sufficiently small that the steps that the bias is less than the variance, and that's all I need. And so we choose it by basically choosing the energy error of being less than 10 to the minus 4.
Right, but you get to know something about the problem to that, right?
Oh no, we run it ahead of time. We run it for a while, and to monitor to get the energy error. Right?
So you're basically okay.
Yeah, this is the. Oh, sorry. Yeah, but basically, yeah. Sorry. Yeah, this is the plot, right? This is the energy error per dimension, right? We say, okay, 10 minus 4, the bias is sufficiently small.
So even if you don't know the distribution, these are all some poses.
It's a heuristic. It's a heuristic thing. Yes.
That's why it's black box.
Yeah. That's why it's auto-tuned. Yeah.
Why are we able to ignore the bias?
Right. We are just saying we're not ignoring the bias. We're just saying it has to be. All it has to be is less than the variance.
Oh.
Right. Let's say it's less than a third of the variance, then it actually doesn't. If you add the two errors in quadrature, right, then it's less than 10% effect on the total error, and it doesn't matter. Right.